All right, this lesson features two smaller topics. So the two smaller topics that we're going to be looking at is we're going to start by looking at the measuring distance in space. So we're going to talk about exactly how far things are away in space. So we all know space is really big, but how big is space and how do we actually measure that distance? So the first way that we actually might measure a distance in space is something that you probably haven't heard of before. It's called an astronomical unit, or the short form for it is AU. So the idea with measuring distance in kilometers is not practical, right? You can't really tell how many kilometers away something is because space is so big. So because of this problem, that's why the astronomical unit was created. What the astronomical unit represents is it's the average distance between the sun and the earth. Now we say average because we know that the earth orbits the sun, so it's different distances at different times, but that average distance of the sun to the earth, that's one astronomical unit. So one astronomical unit is about 150 million kilometers. So it's much easier to say 1 AU than 150 million. That's why we use the astronomical unit. So it also puts in perspective the difference in terms of planets. So if something has an astronomical unit less than one, it's closer to the Earth, it's closer to the sun than the Earth is. So for example, Mercury has an astronomical unit of 0.39 AU. It's closer to the sun than the Earth is because its astronomical unit is less than one. Mars has an astronomical unit of 1.52. Since it's greater than 1, it means it's further away from the sun than the Earth is. And it's just kind of a great way to put things into perspective. The other term that you've probably heard of is you've probably heard of light years. So if you watch any sort of like space TV or space movies, they always talk about light years. Light years are used to measure things outside of our solar system. So inside of our solar system, astronomical units work great. Outside of our solar system, things are even bigger. Things are even further away. So astronomical units really don't make sense. So instead, we developed the light year. The short form for light year is LY. 1 light year is the distance a beam of light can travel in 1 year. It's literally a light year. So it's how far light can go in a year. We talk a little bit more about the speed of light next year in grade 10 physics, but know that light is extremely fast. So in 1 year, light year can actually travel about 9,000 billion kilometers. That's a really big number, or about 63,000 AUs. So again, the light year is much bigger than 1 AU. 1 light year is about 63,000 AUs, and it's much, much, much bigger than kilometers. It's 9,000 billion kilometers. So it just makes more sense to use than kilometers or astronomical units. And again, light years is used to look at faraway galaxies. It's used to look at things that are outside of our galaxy, outside of our Milky Way. The next kind of mini topic we're going to talk about in this lesson is something that's called the models of planetary motion. So I already mentioned that we know that planets orbit the sun. We didn't always think that though. So there were actually different ideas of the model of planetary motion. So the first model, it's outdated now. Some people still believe it, but the original model that we used to think about was called a geocentric model. So for those of you studying geography, you know that geo essentially just means Earth. So a geocentric model meant that we thought that Earth was at the center of our solar system and that everything else actually orbited around us. So not only did the moon orbit around the Earth, which we know is true, but we also thought Venus, the sun, and Mars also orbited around the Earth. Now, this is pretty outdated. This was about 2,000 years ago, and this was just based off the evidence they had at the time. They'd look up at the sky, and they'd see the sun moving, and they'd see the moon moving, so they just assumed that everything was actually orbiting around the Earth. Now what we have is something called a heliocentric model. So a heliocentric model, helio actually just means sun. So a heliocentric model is our sun-centered model, and it was revived by Copernicus. So Copernicus was the first one that suggested it, and he suggested that we have the sun and that the planets actually orbit the sun. So Mercury, Venus, Earth, Mars, the planets actually orbit the sun. Now remember, there are things that can orbit planets. They're called satellites, but the planets themselves are actually orbiting our star, and our star is called our sun. There's two key pieces of support for our heliocentric model. The first key piece of support is something called our orbital radius. Now, an orbital radius is the Each planet has a different orbit, and they orbit around the sun at a different orbital radius. So essentially, an orbital radius is how big the radius of an orbit is. So it's a little bit easier to actually look at it with a picture. Let's look at the first one you can really see in this picture is Earth. So we can actually see Earth's orbital radius. So Earth's orbital radius is essentially how large its orbit is. Whereas after Earth, we have Mars. You can see Mars's orbital radius. You can see Jupiter's orbital radius. You can see Saturn's orbital radius. So essentially, the shorter the orbital radius, the closer you are to the sun. The larger the orbital radius, the further away you are from the sun. So planets that are further from the sun, like Uranus, like Neptune, and like Saturn, are all going to have larger orbital radiuses. Planets that are much closer to the sun, like Mercury, Earth, and Venus, are going to have much shorter orbital radiuses. So the shorter an orbital radius, the faster the planet moves in its orbit. So essentially, we're actually able to track how fast a planet moves based off how many times it'll pass by Earth. Based on this observation, we were able to figure out that some planets will actually orbit quicker, like Mercury and Venus, than other planets that we see less often, like Jupiter and Saturn. This led to the idea of the fact that, well, if some planets are going faster, there must be different orbital radiuses, and that helped us to build that sun-centered model. The other key piece of support is this idea of an elliptical orbit. This was noted by Kepler. So Kepler noted that orbits are ellipses and not circles. So essentially, you actually don't have a perfect circle. Since you don't have a perfect circle, it's actually more of an ellipse. So ellipse is almost more of an oval shape. How did this help the heliocentric model? Well, because when the model was first coming out, a lot of the people that were disagreeing with the heliocentric model said, well, the heliocentric model doesn't match what we see for our planets already. We're seeing planets are actually coming by at different times than we would expect, and Kepler's the one that figured out that's because the orbits are actually ellipses. So before we thought orbits were circles, now we know orbits are actually ellipses, and that helped to perfect the timing, and they were able to better match the observations of what they expect and what they actually saw. So once Kepler came up with the idea of the elliptical orbits, the evidence lined up, and we started to accept the idea of the heliocentric model, or the idea that the sun is actually the center of our solar system. So those were our two short little mini lessons. Next up, we're going to be talking about stars and the life cycle of stars. And we're also going to be talking about a very important star known as our star, known as the sun.